Hi everybody, welcome back. I've described this class, several times as being about the theory of calculus, understanding what's really going on when we do calculus. And this lecture is a great example of that. So in the last few videos, we've talked about, what it means for a sequence to converge, all of the definition of what that means and how that works. So in this video, we're going to prove some of the calculus-y theorems and explain now why all of that stuff has to work the way that it always did back in calculus. So, first most obvious theorem that you need to prove about how sequences converge is this one. And this is something you'd see in every calculus book. As soon as you talk about what a sequence is, then they state something like this. This says that that the sum of the limits is the limit of the sums, and all those sorts of ways of saying this. In other words, if you have a sequence Sn that converges to some S and Tn that converges to some T, then if you add the two sequences together, well, then they'll still converge, and the limit will be S plus T. Or if you take some real number and multiply it by a sequence, then that sequence will still converge, again, if it did in the first place, and you'll just get k times what it converged to. Or if you multiply two sequences together, if they both converge, then when you multiply them together, they still converge, and the limit will be the product of what they converge to. The last one's a little trickier to state because we're dividing. So if you take one sequence and divide by another sequence, then it will converge to the limit of the first sequence divided by the limit of the second sequence, assuming of course that we don't accidentally divide by zero anywhere. So we have to be careful to say that the sequence in the denominator is never zero, and it doesn't converge to zero, so that we're not accidentally dividing by zero when we do this. But these are all things that of course should be true about limits. In fact, if you taught a calculus class and you just showed the limit stuff to students, they would just assume this had to be true, right? If you give them two things added together, they would just do each one separately and add them together because they wouldn't know any different. They would just assume that's how it worked. And of course, it does. But what we're after here is really understanding why that has to work. I mean, throughout your mathematical experience, I know there have been lots of places where things surprised you. Maybe if you think back to the section on cardinality, that was all very surprising. There's been places in this class where we ran across things that were shocking. This, of course, isn't one of them, but until we prove it, we don't really know that, right? I mean, obviously, this sort of limit rules should work, but part of the goal of this class is to understand the theory behind calculus, why things really work the way they do. And so we're going to start by proving all of this. So first up, let's prove the sum rule, right? That the limit of Sn plus Tn, assuming that Sn converges to S and Tn converges to T, should be S plus T. In fact, what we're saying is two things. Not only are we saying that the limit is S plus T, but we're saying that the sum of Sn and Tn converges, period, right? So of course we'll show both things together because we'll show, using the limit definition, that this thing's going to work. And here's the idea. So normally we would at this point do some scratch work, right, to show that things work. So I'm going to sort of tell you, think of this as the scratch work, why this should work. And here's the idea. You know, if the SNs are converging to S, right, then that means that we should be able to get SN with an epsilon of S. Okay, and if you get the TNs with an epsilon of T, well then what does that tell you about Sn plus Tn? Well, Sn plus Tn would have to be within two epsilons of S plus T, right? You just add those together. Right? So that's the idea. Right? All we have to do is get Sn really close to S, get Tn really close to T. Then when we add Sn and Tn together, that'll have to be really close to S plus T. Now, there's a trick here, of course, and this is one reason why I've wanted to show you this slide, and we think of this as sort of scratch work, because if we're going to do the proof and have it come out to look nice, I would like to do my whole fix an epsilon, get a capital N, blah blah blah, and at the very end have um, my implication there, right? The string of inequalities we always get at the end of one of those proofs turn out to be an epsilon, not this 2 epsilon that I've talked about here. So there's a cool trick here that we need to learn how to do, and we'll see this lots and lots of times as we go throughout the rest of this material. And so this is this trick, right? I don't necessarily have to use epsilon, right, if I know my sequence already converges. Because remember, if I know that Sn converges to S, then the definition says for every epsilon, blah, 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 blah. Well, epsilon's a variable there, it's a placeholder. So there's no reason why I couldn't say for every whatever and use something different in that place. There'll be a capital N so that whatever happens. So here's the trick. I'm going to say it this way. Suppose that Sn is not within epsilon, but's within epsilon over 2. And let's say that Tn is, instead of being within epsilon, that it's within epsilon over 2. Well, then what difference does that make? Well, the sum, Sn plus Tn, will now have to be within epsilon over 2 plus epsilon over 2, which is epsilon of S plus T. Right? So, again, if this bothers you when we get to the proof, go back and rewatch the last 30 seconds or so, and make sure you're okay with this idea. Right? This is essentially our scratch work. That if Sn is within epsilon over 2 of S, Tn is within epsilon over 2 of T, then when we add Sn and Tn together, that'll be within, well, a whole epsilon of S plus T. And this will let us get you know, a nice epsilon at the end, not some weird multiple of epsilon. And this is this trick of making something be within half an epsilon because we know that it converges. We'll use this trick a lot. Okay, so let's see how the whole proof goes now. First, we're going to fix our epsilon. Then we need to get our capital N's. Well, okay, from the S's converging, I know there'll be a capital N that we can use with the S's. And so what I'm going to do, so that I can keep all of this straight, I'm going to write a little subscript there for the S to be the capital N that comes from the S sequence. Okay? So there'll be a capital N sub S, so that whenever little n is bigger than or equal to capital N sub S, then the S sequence behaves. In other words, the distance from Sn to S is less than epsilon over 2. But there's no reason to think that the same capital N works for the T sequence, right? So there presumably could be a different capital N. We'll call it capital N, and I'll write a little subscript T there to keep straight which N I'm talking about. So it's some capital N sub T that will now play the same trick with the T sequence. In other words, whenever n is bigger than or equal to capital N sub T, then the distance between T sub n and T will be less than epsilon over 2. And again, there's no reason to think that the SNs get close to S just as quickly as the TNs get close to T. We haven't assumed that these sequences are related to each other at all. So one of these might converge faster than the other one, which means that one of the two ends might be bigger or smaller than the other one. We don't know. That's why we need two of them. We'll have one that goes with the S's, one that goes with the T's. And you could decorate these in lots of different ways. But I think that you could call it N1 and N2 or whatever. But I think it helps to label these capital N's with like N sub S and N sub T, so we remember which one goes with which. Okay, next up is another really cool feature of this proof, and one thing that we'll see again in lots of different places. What we're going to do is let capital N be the max of N sub S and N sub T. Right? In other words, we take the biggest one. The reason for doing this is now if little n is bigger than or equal to capital N, then little n will be bigger than or equal to both N sub S and N sub T, because capital N without the subscript was the biggest of those two. So I can use both pieces, the S part and the T part, so long as little n is bigger than the maximum of capital N sub S and capital N sub T. So that's what we're going to do. We'll start out by writing our big string of inequalities, and we'll be able to use both pieces, the S piece and the T piece. Okay, so I need to show that the sequence Sn plus Tn converges to S plus T. So it's the standard sort of thing. Sn plus Tn is my sequence, S plus T is the limit, so I need to take the absolute value of the difference between those two. Now, okay, that doesn't necessarily look obvious what I want to do with that, right? Because somehow or other, I really want to get the S's by themselves inside an absolute value and the T's by themselves inside an absolute value. So how am I going to make that work? Well, the first step is let's recombine our terms here. So I've color coded things with the SNs in purple and the T's in this light blue. So let's recombine things so that the S's go together and the T's go together. So so if I distributed that minus sign through the parentheses there, I would have a negative S and a negative T, and so I'll move things around so that I end up with Sn minus the S, and then I'll put the T in minus the T separately. So when I do that, I'll just rearrange those. That gets my S's grouped together and my T's grouped together. Now, written that way, it doesn't look so much nicer, right? Everything is nice and color coded and looks cooler. This starts to match what we have, um, you know, earlier, because we know that the SNs are converging to S and the TNs are converging to T. We're sort of just one step away from being able to plug in our epsilon over 2's. And the one step that we need is the triangle inequality. So remember when we talked about absolute values and how all that worked, we had a big deal out of the triangle inequality. And I said in a lot of ways, analysis is sort of the study of the triangle inequality. And now we're going to see why. What we're about to do next, we will do over and over and over and over and over again. Right? We have two things inside that absolute value, and I need to separate them into two different absolute values because I can control how close Sn is to S, and I can control how close Tn is to T. I know that both those things are within epsilon over 2 of each other. So the triangle inequality is what's going to let me break that one absolute value into the sum of two other ones. So there we go, right? The triangle inequality says that the original absolute value is less than or equal to the absolute value of the Sn minus S plus the absolute value of the Tn minus T. Each of those we know is less than epsilon over 2 because we know that each of those sequences are converging. Sn's converging to S, Tn's converging to T, and so I use what we know about them converging, and by using my trick of using epsilon over 2 instead of epsilon earlier, now I have an epsilon over 2 plus an epsilon over 2, which of course gives me epsilon, and voila, there we go. We've used the definition of convergence of sequences to prove that the sequence Sn plus Tn converges to the number S plus T. Okay, next thing you want to show is how multiplying by a k, you know, just taking a sequence, multiplying it by k. If the sequence converged, then multiplying by k doesn't change that. It'll still converge, and it'll converge to k times the limit, k times s, if s was the limit in this case. Now, speaking of cases, this is a great place to refresh our memory of how different kinds of proofs work, is this is going to be a proof by cases, right? So there's really two things we have to think about here, and it may not be obvious that you do, but maybe when I start to show you, you'll see. First off, the first case, what if k were 0? Well, if I multiply Sn by 0, then my sequence just becomes 0, 0, 0, 0, 0, which obviously that converges to 0. And so if I multiply 0 times s, I'll still get 0. So if my k is 0, the whole thing just becomes a whole sequence full of zeros converging to 0. So this works, right? This is clearly true when k is equal to 0. So that's my first case. The second case is when k isn't 0. Right? And the reason I have to do this into the two pieces is you'll see in just a second. I'm going to divide by k in just a second, and I don't want to be dividing by 0. So if we handle the 0 part first, which is obvious that that works, then in the next part of the proof, the entire rest of the proof. We're in the second case where k isn't 0, and thus when I need to in just a second, I can divide by it. Okay, so we're going to do the standard definition of convergence here. So I need to fix some epsilon, which is greater than 0, and somehow manufacture myself a capital N. Well, I know that the sequence Sn was converging to S. That was what we were assuming in this theorem. So using the fact that Sn is converging to S, there has to be a capital N, right? And that capital N will make the distance between Sn and S be less than, well, whatever I want to put here. Remember, we saw in the last proof, we don't have to put an epsilon there. If we know this sequence converges, right, then this works for every number I want to put in there as an error bound. I don't have to just always use the letter epsilon. I can use whatever number I want to. That's the point. So in the last proof, I did epsilon over 2. Now I want to do epsilon over absolute value of k. So because I know the SNs converge to S, there is this capital N, so that whenever little n is bigger than or equal to capital N, absolute value of Sn minus S is less than whatever I want to put there. And the thing I want to put there is epsilon over absolute value of k. And the reason is, if then I start checking what happens to the sequence k times Sn. Right? Well, want to show that that converges to k times s. So I take the absolute value of ksn minus ks. And of course, it's just screaming to factor out the k, right? And I can do that. Of course, I'll factor out inside the absolute value, so I can separate those into two different absolute values, and I'll have an absolute value still around that k. Notice this is why that absolute value that k had an absolute value around it just a second ago when I was messing with the epsilon. Because now I know that when little n is bigger than or equal to capital N, my purple Sn minus S, that will be less than epsilon over absolute value of k. And with the absolute value of k in front of that, those cancel and the whole thing just leaves me with epsilon. So perfect. There's my proof by cases, right? That k sub Sn has to converge to ks. Now, corollary. Remember what a corollary is? A corollary is like an obvious sort of theorem that we get almost for free once we've proved something else. So we've proved that the sum of sequences worked, and we proved that multiplying by a number worked the way we always thought it would. So we don't really have to do any work to prove that subtraction works. Why is that? Well, this is just a combination of those last two things. Because if I have an Sn that converges to S and a Tn that converges to T, then what I could do is take the Tn and multiply that by a minus 1. That'll converge to negative T. Then if I take the sequence negative Tn and add that, notice I'm adding now, that to Sn, that's a rule I already know. So that'll converge to S plus negative T, which of course is S minus T. So we get subtraction for free as soon as we know multiplication and addition work the way they're supposed to. At least multiplication by a constant, K. So to show that multiplying two sequences together still works, right? Then we have some proofing to do. So suppose we have our sequence Sn converging to S and Tn that converges to T. When we multiply them together, you ought to get something that converges to S times T. Now this is another place where we'll need to do proof by cases, although the first case is pretty straightforward, and we're going to do that really quickly again. So first possibility, what if the T were 0? So the Tn's sequence is converging to 0. Okay? So that means the limit of Sn times Tn should be S times 0. So I should get 0 out of this. Well, notice that since we already know that the SNs converge, they have to be bounded. Right? And it's not hard to show, and I will leave it for you to show. If you get stuck, email me and I'll go through all the details. But I want you to have a chance to play with it because it's very easy to prove that if you have a bounded sequence times a sequence which converges to 0, then that new product has to converge to 0. And again, it's very straightforward, and you can do that with a straight definition of what it means to converge. So that's the first case, that t is 0. Then the second case where t isn't 0 um, is the more important one by far, and we'll spend most of our time talking about that. But why do we have to separate this out? Well, of course, because I'm going to divide by t in just a second, and I want to make sure that I've taken care of the possibility of accidentally dividing by 0. So, okay, so the main part of the proof, we're going to use another very, very cool trick. So again, if you remember this proof, don't think so much about the cases part. This is the most important thing. Here we go. Let's fix our epsilon, right, and proceed through the using the definition. Now, as we said before, since the SNs converge, it's going to be bounded. What does that mean? That means that there's some capital N, so that the absolute value of the SNs are always less than or equal to the capital M. It's true for every N. Every element in the sequence, is bounded by M like this. Okay, that's true because Sn was a convergent sequence. All right. Well, now we can pull out again our definition of convergence, that we know that the SNs are converging to S, the TNs are converging to T. So, as soon as I have an epsilon on the screen, that means that I can get my capital N. Because we already know that these are converging, we know there'll be a capital N that goes with the S and a capital N that goes with the T's. So with the S part, there'll be a capital N. I'll write capital N sub S to keep it straight, so that whenever the little n is bigger than or equal to the capital N sub S, then the distance from Sn to S will be less than, and again, I can put whatever I want to right there. Because remember, the definition said for every epsilon, and epsilon is a variable in the definition, right? I can put any number I want to right here because I know that the SNs are converging. And as soon as I know that these have to converge, then this has to work no matter what I put on the end of that line. We've seen that before with epsilon over 2, with epsilon over absolute value of k. Now the trick, and again, it's not obvious why this has to work. You'd figure this out in the scratch work, but I don't want to show you the scratch work because I want it to be a surprise. The magic thing that goes here to make this work is going to be epsilon over 2 times the absolute value of t. And again, that's why I separated out the possibility of t being 0 earlier, so that we're not dividing by 0 there. On the other hand, I can play the same game with the t's, and I'll get a capital N sub t. Now, whenever little n is bigger than capital N sub t's, then the t sub n minus t, take the absolute value, that ought to be less than, well, I can put whatever I want to on the right hand side, as long as it's positive. And so I'll use epsilon over 2m. Right? And so, again, why does that work? Well, I'll show you. So we're going to get our capital N like we've done before by letting it be the maximum of both of these other n's, so that now whenever little n is bigger than my single new capital N without the subscript, it'll be bigger than both n sub s and n sub t, so I can use both of those lines above that to make this work. So okay, so let's erase the screen so we have some more room here. So if the little n is bigger than capital N, both of those things are in play. That's awesome. But look at what I'm trying to prove. I'm trying to prove that the sequence, which is now Sn times Tn, right? That's the sequence I care about, not just the Sn's by itself or the Tn's by itself, but what I get when I multiply that together and get a new sequence, Sn times Tn. I need to show that that converges to St. That's my new limit. So I have to subtract those two, take the absolute value, and then eventually get less than, blah, 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 epsilon. Okay, well, in the first proof we did when we were looking at the sum of two sequences, it was pretty obvious how to separate things out, and we could hit it with the triangle inequality. Here, okay, I can separate it out by by spreading them out, right? By moving them to opposite sides of the absolute value. But it's not obvious how that's going to help. So a super important trick happens here, and I call this a trick because it's not something that's obvious or what you would think of doing. So it's important for me to show you one of these so that you'll see, because we're going to use this idea a lot, and you kind of have to have seen it once to realize that doing something like this is a possibility, and it's kind of sneaky. What I'm going to do is in that blank white space that I've opened up, I'm going to add and subtract the same thing. I'm going to add and subtract Sn times T. Okay? So I haven't changed anything in the in red there. I have a SNT, and then a minus SNT. So I didn't change anything. Okay, everybody's with that. I haven't changed anything. But by adding and subtracting this SNT, it lets me group these two things and hit it with the triangle inequality. So what I'm going to do is take the triangle inequality now and take the first two things inside the absolute value, the SNTN minus the SNT, break that off into its own absolute value, plus, and then take the last two things, SNT minus ST, break it off into its own absolute value. Okay? So again, this is just the triangle inequality, breaking up two things. I'm breaking them up at that red plus sign, okay, into two separate absolute values. But by doing it this way and by adding and subtracting that SNT, something really cool happens. Because what do I have now inside those absolute values? Each of those absolute values now has something I can factor out. So if you look at the first one, I have SN minus SNT. So there's an Sn which is common to both of those, and I could factor absolute value of Sn out. In the second absolute value, I have SNT minus ST. And notice the T is common to both of those. So I could factor the absolute value of T out. So now I'll change the colors back so they sort of match a little better. So when I do that and factor out the common thing to each of those, the first absolute value will have an absolute value of Sn times absolute value of Tn minus T. The second one gets an absolute value of T factored out times Sn minus S inside its own absolute value. And now if you look at those, again, maybe the color coding helps or maybe not, but if you look at those absolute values there, the differences are exactly what you have when you prove that Sn converges to T and that Sn converges to S. In other words, I already know stuff about that. I already know that Tn's are getting closer to T and that Sn's are getting closer to S, and so we can use that. Right? So before I throw that in, to do one other thing, what do I know about the SNs? Well, we said at the beginning, SNs were converging, so we could use the definition and stuff, and we will. But we also know that because they're converging, the SNs are bounded. So the biggest that the absolute value of Sn could be is m. What about the t? Right? Well, let's just leave that there for now. Okay? And now hit it with the definition of convergence so that I can replace absolute value of Tn minus T and absolute value of Sn minus S with what we decided a few minutes ago. And remember, we don't want to use epsilon, we use something different. For Tn, we used one thing, for Sn, we used a different thing, and now we see why. Because what we used on the last slide there, again, if you're not sure, rewind the video here for a couple of minutes and you go back to see what the calculation we used before was, we had absolute value of Tn minus T should be less than epsilon over 2m. And for the s's, we did absolute value of Sn minus S should be less than epsilon over 2 absolute value of T. And again, see, this was rigged up exactly because I knew I was going to get to this point. Because now the m's cancel, the t's cancel, and I end up with half an epsilon plus half an epsilon, which altogether everything cancels and gives me one glorious epsilon. So again, this was long and complicated, and this adding and subtracting the right thing in the middle so that you can do the triangle inequality and separate things out. It's tricky and not obvious at all that that should work, but it does. And that's a tool you want to keep in your toolbox, right? To pull out if you need it, because there'll be places where we'll have to do this a lot through the rest of the material we're going through, where we add and subtract the same thing so that then we can break the absolute values up into two different pieces and then proceed to factor out things and estimate things and eventually end up with our epsilon. Okay, we've talked a lot about convergent sequences. Now we've proven most of that first theorem we had. I'm not going to prove the division part because it works very similar to what we've done so far. I think everybody kind of gets the gist of it. And more importantly, I've shown you the important tricks. So what we haven't talked about yet are sequences that go off to infinity or to minus infinity. So let's get a definition for those. So if you have some sort of a sequence Sn, it diverges to infinity. Notice I'm going to be careful not to say converges to infinity because you know it doesn't really fit the definition we've already used for convergence, right? So we'll say it diverges but goes off to infinity as it does it, right? Diverges to infinity if, well, if you look at the structure of this, it looks an awful lot like what we've had before, you know, for converging. For every, instead of epsilon, we have for every m contained in R, there's a capital N again, right? So that whenever little n is bigger than or equal to capital N, then something happens. In this case, the terms in the sequence, SNs, they're all bigger than m, which makes sense because if this thing's going off to infinity, then no matter what number you give me, capital M, I'll eventually get bigger than that in my sequence, right? So in other words, you give me as big a number as you want to, and if my sequence really does go to infinity, at some point it'll get bigger than that number and stay bigger than that number. That's what the definition says. The definition of diverging to negative infinity works exactly the same way, only that last inequality is flipped. So if something's going off to minus infinity, you can give me as small a number as you want, or if it helps, a big negative number, right? Then eventually the terms of my sequence will all get smaller than that big negative number and stay there. Now, if we look at this definition closely, right, you'll see that the structure is exactly like the structure for the definition of convergence of a sequence. We have a for every m now instead of for every epsilon. Then we have to show that there exists a capital N, just like before. And then we have this implication to prove. And so we'll do an example. We'll do it exactly the way we were doing the last ones, where we first pick an arbitrary capital M, then we produce a capital N. That's a constructive existence proof. And the last part, proving this implication, that's we'll just do a direct proof, assuming that little n was bigger than or equal to capital N, and showing that Sn has to be either bigger or smaller than m, depending on which definition I'm using. So let's do the diverging to plus infinity first. We'll do an example where we have, say, 3n plus 1. So we want to show that that goes off to infinity. And of course, obviously it does, right? When n gets really big, 3n gets really big. Adding 1 makes it even bigger. So obviously that should go off to infinity. But again, we're doing the theory behind calculus. We're proving things. So we don't want no surprises, right? We don't want any surprises here. And as we've seen earlier in this class, there can be surprises. So we're ruling them all out by doing everything slowly and carefully, making sure it all works the way we think it does. So how do we do this? It's the same structure we've had before. I'm going to fix this time a green capital M instead of an epsilon. Because again, the idea is before where epsilon was my error bound, telling me how close I wanted to get to the limit. Now we're going off to infinity. M is sort of like my bound that keeps me from being small. If we're going off to infinity, I ought to be able to beat any bound you give me. That's the idea. If m is some bound, I ought to be able to get bigger than that, go off to infinity. Right? So fix my arbitrary capital M. Now let's pick some capital N, and the right capital N to use is some positive integer bigger than m minus 1 over 3. Okay, how do I know that? Well, I should have figured that out on Scratchwork, and I did. That's how I got it. I won't show you all that because we've worked out how you do that sort of thing before. And again, if you get stuck, always email me or call me. We'll go through the details. But you figure that out exactly like we've always done. Right? And you'll notice that, again, the structure of the proof is exactly the same kind of thing we've done before. First, we picked an arbitrary capital M. Now we show that there exists a capital N. Right? And then we just do the proof of the implication. So let's assume that little n is bigger than capital N. Then, well, what have I got to do this time? I have to prove that 3n plus 1 is bigger than m. So what do I do? Well, instead of going less than, less than, less than every time, now I'm showing that this goes off to infinity. So I need to show bigger than, and bigger than every time. Right? I need to show that 3n plus 1 is bigger than m. So little n is bigger than capital N. So if I replaced my 3n, that's a little n, with 3 big N, then I get bigger. Um, well, now what do I know about capital N? It's bigger than m minus 1 over 3. So if I replace capital N with m minus 1 over 3, I get bigger still. But of course, now notice what happens, right? This is why I picked m minus 1 over 3, because the 3's cancel, and then the negative 1 cancels with the plus 1 that's outside the fraction, and that all just reduces to m. So all of that together is the proof of the implication part, just like we've always had. So the structure of writing a proof that some sequence diverges to plus infinity or diverges to minus infinity is exactly the same way we did it before. First, you do your scratch work, which of course I didn't show you here because you already know how to do the scratch work and to figure things out, and nobody wants to see that. And so then we go through and we work the problem the same way. We fix our capital M, we show that there exists a capital N, and then we do the proof of the implication that all that just works. Okay, another theorem that again, this should be kind of obvious, and the proof will be fairly short. Right? Suppose that we have two sequences, an AN and a BN. The AN is smaller than the BN, or at least less than or equal to the BN for every N. Okay? No matter what N I have, AN is less than or equal to BN. So all the terms of the AN are smaller than the corresponding term for it in the BNs. What can we say about that? Well, suppose that the ANs diverge off to infinity. Well, the BNs are even bigger, so of course they go off to infinity. On the other hand, if the BNs drop off to minus infinity, the ANs are even smaller, so of course they drop off to minus infinity. So, okay, so how do we prove this? Well, again, this is mostly just an exercise in using the definition. Right? So how do I prove that first part? Well, first I need to fix a capital M. That's my first step in using the definition. Then I need to somehow gather up a capital N. So how do I do that? Well, because I know that the smaller sequence a sub n is diverging off to infinity, there's a capital N that works for it. There'll be a capital N so that whenever little n is bigger than or equal to capital N, the a sub n's are bigger than m. Right? So that's perfect because the b sub n's are even bigger. That was the point. The b sub n's were bigger than the a sub n's. So what that means is whenever little n is bigger than or equal to capital N, b sub n is bigger than a sub n, and a sub n was bigger than m. And there we go. And again, you see the structure of the proof, right? I fixed some arbitrary m. I showed that there existed an n, and then I worked through the implication and showed that the n did what I wanted it to. Exactly the same idea we've used before. Okay, so that's the first part when we have a sequence that where the small sequence goes to infinity. The second half was when the big sequence goes to minus infinity. That's the second part. And of course, that one is homework. So the proof works, of course, just like the one we did on the screen a few minutes ago. It's just that the inequalities are all going to run the other way. So I'll let you play for that with that for homework to make sure that you understand exactly how that works. Another theorem. Let's suppose that we have a sequence of positive numbers. Now, the positive is important here. Okay, that's really important. If Sn is a sequence of positive numbers, then Sn diverges to positive infinity if and only if the limit of 1 over Sn goes to 0. Okay, why was the fact that Sn was a sequence of positive numbers important? Well, you can see that 1 over Sn would go to 0 even if Sn wasn't positive, even if it went to, say, minus infinity. Okay, um, but because I wrote this with an if and only if, I needed it to go the other direction. Right? So that's why I needed to assume that my sequence was positive. Again, you could play this with negative numbers too. If you knew your numbers were all negative, then going off to minus infinity would be the same as the reciprocal 1 over Sn converging to 0. And again, this makes perfectly good sense, right? If Sn is getting really big, 1 over Sn should be getting really small. So, how do we prove this? Well, this was an if and only if, so I have to assume one and prove the other one. You remember how all of our working on logic and how the proofs work. So I'm going to do one direction first. I'm going to assume that the SNs diverge to infinity. And then we need to show that 1 over Sn converges to 0. So how do we do that? Well, we just use the definition, right? We fix our epsilon, and I'm going to let capital M be 1 over epsilon. And so as soon as I have a capital M, I can use the fact that I know that the sequence Sn diverges to infinity to get a capital N. Because since the Sn's go off to infinity, there will exist a capital N, so that whenever little n is bigger than capital N, the Sn's are all bigger than capital M. So great. Now we just need to do the reciprocals to this, right? So now whenever little n is bigger than or equal to capital N, then the reciprocal, 1 over Sn minus 0 inside the absolute value, which of course I can ignore the 0 when I subtract it. And I don't need the absolute values because we assumed that the Sn's were positive. Remember, that was important. Now 1 over Sn, well, that'll be less than 1 over M because that's the inequality we had earlier, and I've just taken the reciprocals. And what was M again? It was 1 over epsilon. So there we go. Everything just flips, and so there's my epsilon. Okay, so it works exactly the way you think it would. Okay, so that's one direction, right? We started out assuming that the SNs diverged to infinity, and we had to show that 1 over SNs converged to 0. For the second part, we have to do it the other way, and that's homework too. So if you have questions about trying to set that up, again, it's almost exactly what we just did. You just do it in reverse. If you have questions about any of that, though, you can always email me, call me. We can video conference, whatever it takes to get your questions answered.